Welcome to an introduction to the definitions of the kernel and image of a linear transformation. Let the transformation T be from vector space V to vector space W be a linear transformation. Then the kernel of T, denoted ker T, is a set of all input vectors V in the vector space V such that T of vector V equals the zero vector. And if we're given T of vector V equals matrix A times vector V, then the kernel of T is equivalent to the null space of matrix A. We can also state the definition of the kernel of T as shown here below. If we take a look at the mapping on the left, because we have a linear transformation from V to W, we know the zero vector in the domain maps to the zero vector in the range or set of outputs, but the kernel of T is a set of all vectors in the domain, or the subset of vectors in the domain where the output is equal to the zero vector in the range. The image of T, denoted MT, is a set of all output vectors T of vector V such that the vector V is in the vector space V, or the domain. And therefore the image of T is equal to the range of T. Given T of vector V equals matrix A times vector V, the image of T is equivalent to the column space of matrix A. And the definition of the image of T can also be stated using the notation shown here below. Going back to the mapping, again, the image of T is a set of all output vectors T of V such that the vector V is in the vector space V. And therefore the image of T is this set of vectors here that are all the output vectors resulting from the input vectors in the domain under the transformation T. I do want to make a note. If we are given T of vector V1 equals vector W1, we say vector W1 is the image of the vector V1 under the transformation T, but notice here we're referring to the image of a single vector, where when we talk about the image of T above, we're talking about the image of the entire transformation. Let's take a look at a couple of examples. Here we're asked to find the kernel of the transformation T from R3 to R2, defined by T of vector x equals matrix A times vector x with the given matrix A. Remember, this is equivalent to determining the null space of matrix A. So for a quick review, to find the spanning set of the null space of a matrix, we solve matrix A times vector x equals a zero vector. The spanning set contains all the vectors x in Rn that satisfy the equation. The spanning set contains one vector for each free variable. If there are no free variables when solving the equation, then the only vector in the null space of matrix A, or the image of T, is the zero vector. So going back to our example, we begin by setting up the equation matrix A times vector x equals the zero vector. Because we're mapping from R3 to R2, we know the input vector is in R3, and the output vector, the zero vector, is in R2. This should look familiar. The next step is to set up an augmented matrix, and then write the augmented matrix in reduced row echelon form. So here we have the augmented matrix, and here we have the augmented matrix in reduced row echelon form. Notice how we have a pivot in column 1 and column 2, but not column 3. Because we have one free variable, there'll be one vector in the spanning set that makes up the null space of matrix A, as well as the image of T. Row 1 indicates that x1 minus x3 equals 0. Row 2 indicates x2 plus x3 equals 0. And because x3 is a free variable, we know x3 equals x3. The next step is to solve x1 and x2 in terms of the free variable x3. x1 equals x3, x2 equals negative x3, and x3 equals x3. Let's parameterize the solution by letting x3 equal t, which gives us the solution vector x equals t negative tt. Factoring out the t, we have vector x, which again is the solution to ax equals 0, is t times the vector 1, negative 1, 1. So now we know the kernel of T, which is also the null space of matrix A, equals the span of the vector 1, negative 1, 1. So because we only have one vector in the span, all the linear combinations of this vector give us all the vectors in the domain of the transformation T that map to the zero vector or have an output vector of 0. And now for the second example, let's find the image of the same linear transformation by expressing the image as the span of a basis. Remember, this is the same as expressing the column space of matrix A as a span of a basis. So for a quick review, the pivot columns of matrix A form a basis for the column space as well as the image of T. We find the pivot columns by solving the same matrix equation, matrix A times vector x equals a zero vector, a basis will be the corresponding column vectors from the original matrix A. And once we have a basis, we can express the column space of matrix A as well as the image of T as the span of the basis. So again, we set up the equation matrix A times vector X equals a zero vector, which we already did in the previous example. Then write the augmented matrix in reducer echelon form. But here's where our work changes. The next step here is to identify the pivots. We have a pivot in row 1, column 1, as well as row 2, column 2, where we have pivots in column 1 and column 2, which means column 1 and column 2 of the original matrix A form a basis for the image of T, as well as the column space of A. So again, now we know a basis for the column space of A, as well as a basis for the image of T, is equal to the set containing the vectors 1, -1, and -1, 2, and therefore the image of T equals the span of the set containing these two vectors, which indicates all the linear combinations of these two vectors will give us all the output vectors T of vector X, given vector X is in the domain or in R3. I hope you found this helpful.